All right, so welcome to the last week of Trig. Holy cow, we almost made it. Just have a few more things that we need to talk about, and then we'll be there. So we've got 2 more days here and then a final exam. But before we get going, just a couple of things. So I graded the exams. Hopefully you guys saw, got those in. But we need to talk about this. Now, obviously, what I'm going to be talking about here is not everyone, but quite a few of you. I gotta say, I'm a little bit upset that so many of you were turning to alternative things to actually take your exam, like specifically identities. I know identities are tough. They are. They're challenging, and sometimes you don't really know where you need to start. And that's part of the point, is to learn how to deal with difficult things, because all of you are going on to calculus, and if you think calculus for a minute is going to be easy, you're fooling yourselves. And it's a lot better to work on that now, to deal with the stress of, I can't figure this out. How do I figure it out? Instead of going and resorting to something online. Specifically, I'm talking about the identity where a good half of you did some crazy stuff with square roots of 2, where you were factoring with the difference of squares of basically one of the double angle identities for cosine. And I'll just tell you, I've been teaching trig for over 20 years. Okay, I started teaching trig in like 1997 or something like that. I have never, with the probably pushing 1,000 students I've had, never had a single person ever even remotely try to do that. Half of you did this. So I knew something was up. So I went and I looked and I was like, oh wow, I had no idea that Symbolab will actually show you how to do identities. I do know that there's a lot of power out there in terms of things, but I thought identities were safe. Here's the deal. I don't give a shit what Symbolab does. I don't care what they think. I want to know what you think. I want to know what you do. And I got to tell you that this is plagiarism. I never once thought I'd have to discuss plagiarism in a math class, but this is plagiarism. I know you probably hear that term and you think about this in like English classes and history classes where you write essays and all that, but plagiarism is representing somebody else's ideas as your own. And when you go to somewhere like Symbolab and you use their steps to walk through it, you are representing their work as yours. And that's not okay. All right. The college takes that seriously. We have in our policies strict rules about plagiarism, and it's a problem. It's a major problem. Now, some of you may not be aware that it's a problem or think that that's plagiarism, but anytime you're using somebody else's work and saying that it's yours, that's plagiarism. Again, I can't believe I have to have this discussion or talk about this, but it's a problem, and you guys really need to not do that. I take it real personally, and I try not to, because I know that's not really the intention. I know most of you that are using those resources are doing it just because you want to make sure you're getting a good grade and you got to get through this class, and it's not, yeah, I want to dick over Bruce, right? Like, I get that, but I do take it that way. And so I'm trying to push past that and just be like honest and real with you guys. Like, I get it. Not everybody loves trig like I do. And that's fine. It's totally fine. But what I'm trying to do in this class is get you guys ready for when you're going to need it in the future. And if you don't have a strong, like a very strong foundation in trig, calculus is going to kick your ass, specifically second quarter. And you don't have to believe me, but I'll tell you what, go talk to those that have gone through it and ask them right? And then talk to students who've taken trig with me versus those that have taken trig with other people. And I promise you, I have a method, I have a plan. And resorting to symbol lab and that kind of stuff is really screwing you for the future. Yeah, I mean, yeah, yay, you get a good exam score. That's not the point. Grades don't matter. Like, they really don't. I know that's easy for me to say because I'm not actually getting grades anymore, but in all of my experience in school, and I did a lot of school, grades really didn't matter, right? The A versus the B, what really mattered is that you know that stuff, especially in math, because we build, right? I mean, think about everything that we do, like with this identity stuff. Think of all the algebra we use. You can't just go, oh, well, I took algebra, now I'm done with it. No, you need to know it so you can do trig. And when you get to calculus, you're going to need to know the trig, just like you need to know the algebra. So here's the deal. I did not like just give people zeros for these things because, well, honestly, it took a while. It took a few of them until I started seeing a pattern for me to try to figure it out. And I don't have time or energy right now to go back and look through everybody's exam and find out who were the ones that specifically were using things. Because again, I know you might want to claim, oh no, I came up with that idea. Don't bullshit a bullshitter. Okay, I know. Like I said, it's been 20 plus years. I've never seen one person do it, and now all of a sudden there's like a dozen. No. Okay, so I'm not gonna penalize you, but I will tell you that on the final exam, I am going to absolutely look and see what every single online program I know gives you as a suggestion for these identities. And I'm going to be looking at them closely because this is nonsense. Do your own damn work. And if you don't know it, don't know it. That's actually good, right? It's good to recognize when you don't know something, because then you can go back and work on it and you can learn it better. All right. This isn't a, let's just get the A in the class. That's the worst thing you could do. It's a waste of college, man. And, you know, also realize that like it's damaging, and it's damaging to me, you know. And at the end of the day, right, like all you have is who you are. You know, other stuff can get taken away. Like, think about what's going on in the world right now, and all these demonstrations and riots and the frustration that people have because of, you know, all the conditions in the world, right? There's a lot of external stuff that you can't control. Yeah, but what you can control is in here and in here, right? So in the end of the day, that's all you got. Don't throw it away. Don't throw that away just for a grade in a stupid trig class. Not worth it, man. Don't throw away your integrity just for that. So anyway, I'm done preaching, and I know many of you this does not apply to. I'm not talking to you guys, right? But to the one, you know who you are, okay? Just, it's a problem, and I'm going to really enforce it now, okay? So anyway, now that I just brought everybody down, I apologize, but I had to get that off my chest, so. But let's actually talk about the trig itself. I'm trying to remember what we were doing last time. Oh yeah, we were doing polar coordinates. We talked about graphing them, and the complex numbers. We have a little bit more to talk about with the complex numbers, but before we do that, any questions about the homework? How's that treating us? All right, so in the absence of comments, I'm going to take that as things are going okay. All right, so let's go back and look at the trig form of complex numbers. And I kind of walked you through multiplication and division and exponents. And I still want to talk about roots, but let me remind you what we did. Okay, so let's go to the board real quick. All right, so complex numbers in general, they have a real part and they have an imaginary part. And so when we write them, we use z as a generic complex number, and we write it as a plus bi. And what we saw is that we can actually think of these real and imaginary parts as living on a plane, a complex plane, where these are x's and these are y's. And if you do that, you can actually convert this into a polar form using the polar conversions. So remember, x is equal to r cosine theta and y is equal to r sine theta. So if you use that, instead of writing it in the rectangular normal form, you can actually write it in this form. So some things to remind you: the absolute value of z thing, we call this the modulus. And it is literally found the same way that we find distances, or that we found r when we were in polar. So it's the square root of a squared plus b squared. Okay, so that's our modulus. And then theta, this is the argument. Call this the argument. And again, we know we can get that by using the fact that the tangent of theta is equal to b over a, so y over x kind of idea. So we just have to make sure that we're using the right theta. Same concern as always when you use the inverse tangent. The angle that you get from that may not be the one that you want. You can just adjust it by adding pi or subtracting pi to get to be where you need to be. Okay, so we talked a little bit about how to convert these, but then the other thing that we saw was that this actually speeds computations. Because if we want to take two of these and multiply them, for example, so if we take z1 times z2, what we do is we take the moduli and multiply them. And then, do you remember what we do with the angles? All right, so Adam, you're exactly right. You add them. So when we multiply, it turns out that we can actually add the angles together. Apologize, I'm running out of some space there. So this can be fast. And what we saw is now we don't actually have to FOIL, right? If you have these two numbers, you have to FOIL and distribute and all that sort of stuff. If they're already in, if they're in this polar form, super quick. You add the angles together, done. Multiply the two moduli, done. All right, well, similarly, if we divided, the trick here is to divide the moduli. And this time, instead of adding the angles, we subtract them. And this is way easier, because when we divide otherwise, we have to do that whole multiply by the conjugate of the bottom, and then distribute and FOIL on top and bottom, blah, 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 right? It's a ton of stuff. This is quick. This is quick and easy. All right, so that was how we do multiplication and how we do division. You either multiply or divide the moduli, and then either add or subtract the angles. But then where this really comes in handy is when we do powers. Because powers is just repeated multiplication. So if we have something and we want to raise it to an exponent, we take its modulus and raise it to that power. And then if you just take that idea of, well, we just keep adding the angle over and over and over for as many as there are, that leads to a multiplication in here. And this is really where it starts picking up speed. If you want to take a complex number and raise it to a power, it's way faster if you're in this polar form. Okay. So that's where we got last time. So what I want to show you then is, what about taking radicals? What if we're going to take a root of one of these things? All right, well, it actually follows pretty directly from powers, because I don't know if you remember this, but if you don't, let me just remind you. If you take a root, that's the same as having an exponent. It's the same as having a fractional exponent. So that's the same as taking z to the 1 over n. So like a square root is the same as a half power, cube root is a 1/3 power, and so on and so forth. Okay, well, if we remember that, then we can actually apply the same thing to get a formula for the roots. So we're going to have the nth root of z. It's going to equal the nth root of the modulus. So whatever the modulus was, take its root. And then, instead of multiplying by n, we're going to multiply by 1 over n. So this becomes theta over n. And I want you to notice that I'm leaving a space. It's intentional. We're going to put something in there because there's a little bit of a trick we have to pull. But we are going to take that angle and we're going to divide it by n. So same thing over here. Again, leaving a little space. All right, so now why the space? Well, if you think about it, if we're going to represent a number in polar form, so a complex number in polar form, there's not just one angle we could use, right? We can take any angle that's actually coterminal to the one that we find. So what we actually have to do is add on a multiple of 2 pi. Now I'm not going to use n because we've already used that for our nth root, so I'm going to put k. So what I've got on top here is theta plus 2 pi k, all divided by n. And that's exactly the same angle that's going to go into that sign. And so what we have to do with that k is just keep varying it. I always start with 0 because it's easy. Then I go to 1, then I go to 2, then I go to 3. And I keep going until I start repeating and getting the same numbers as before. Now, it turns out that it's really easy to determine how far you have to go. All right, you're going to go k equals 0, 1, 2, dot, dot, dot. And the last one you're going to do is n minus 1. So like if this was a 5th root, the last one you plug in is 4. If it's a square root, the last one you plug in is 1, and so on and so forth. All right, so let me show you how this works. It's actually not terribly difficult. It's really just a matter of keeping track of where you are. Make sure you catch all of the roots. But before I do that, let me just give you the name. This is actually named after a French mathematician. And it's de Moivre's theorem. I don't really know French, so I just kind of fake it, but it's de Moivre's theorem. So if you ever see that, it's really just the theorem for finding roots of complex numbers. So we're going to start off really easy. Okay, we're going to take an angle or a number whose angle is pretty easy to get. And we're going to try to figure out the square roots of I. Okay, so here's our question. What are the square roots of I. Now, I, we already know, comes from a square root. It's the square root of -1. But I just want to know what's the square root of I. So we're going to use this. So what we need to do first is figure out a modulus and an argument. So how far away this point is from 0 and in which direction we go. So that way we can plug those in for our theta and our absolute values. So let's plot z equals I. So z equals I is going to be right up here. So remember how this works. The x direction is our real part, and the y is our imaginary part. So there is no real part to this. It's only imaginary. So we're just going to go up, and we're going to go up one step so that we're at I. All right, so what this tells me then is that the modulus of this is 1, because we are one step away from the origin. I also know that my theta, I mean, I have lots of ways of representing it, but I know that theta equals pi over 2. And that's probably the easiest one to do. All right, so we got all the information we need. So since we're doing square roots, that means that n equals 2. So when we plug in our k values, we're going to plug in 0 and we're going to plug in 1. Okay, so as you said, if it was at 1, 0, would the modulus still be 1? Yes. Yeah, if we were over at this point, the modulus would still be 1. Same thing if we were back here, the modulus would be 1. If we were down there, the modulus would be 1. So direction does not matter. Nope, it's only how far away are we. All right, so let's jump in here and let's use de Moivre's theorem. All right, so here's root number 1. All right, so here's what I'm going to get. I'm going to have the modulus, but the nth root. So we're doing a square root, so I'm going to get, I'll call it here, let's call it R1. It's going to be the square root of 1 times the cosine of pi over 2 divided by 2. And then plus I times the sine of pi over 2 divided by 2. So again, just look at what I'm doing. So n is 2 because it's a square root. So that's why in the bottoms here I have 2. For my argument, or sorry, my modulus, how far away I am, it's 1. So I put a 1 there. And then the angle, I start with pi over 2. All right, so remember that's letting k equal 0. Okay, so this would then be, square root of 1 is 1, so we'll just leave that. But this is the cosine of pi over 4 plus I sine pi over 4. And this is actually a nice, nice angle, so we could actually calculate that. So we get root 2 over 2 plus root 2 over 2 I. Okay, so then where did I get 2 for n? Is that it's a square root, and the index of a square root is 2. So like a cube root, the index is 3. A fourth root, the index is 4, and so on. We'll do a cube root next. So you'll see where one where n is equal to 3. All right, so there is the first of the square roots of I. Okay, so if you were to take root 2 over 2 plus root 2 over 2i and multiply it to itself, you're going to get I. Right, that's the whole point of square root. All right, well, let's look at root number 2. So for root number 2, not much changes here. Okay, so we're going to R2. It's going to still be the square root of 1 because it's still a square root. We're still having a modulus of 1. But now inside of our angle, I'm going to have pi over 2 plus 2 pi divided by 2. So the theta is still pi over 2. That's the angle we found. But now I'm going to add 2 pi because that's also coterminal and so can lead to another solution. Okay, well, the same thing's going to go in here. So pi over 2 plus 2 pi over 2. So this is k equals 1. So I started with k equals 0, then I went to k equal 1. And this is as far as I'm going to have to go because a square root, there are only 2 square roots. Okay, well, let's see what this looks like. So the square root of 1 is, of course, 1. And what we're going to be left with is, well, 2 pi plus pi over 2 is 7 pi. And so this is going to be 7 pi over 4. I totally lied. How about 2 pi plus pi over 2 is 5 pi over 2? This is 5 pi over 4. Apologize for that. So that's cosine of pi over 4. And again, plus I sine of 5 pi over 4. And just like before, those are angles that we know. So if we go ahead and calculate that, the cosine of 5 pi over 4 is a negative root 2 over 2. The sine of 5 pi over 4 is also a negative root 2 over 2. So we get that the second square root of I is negative root 2 over 2 minus root 2 over 2 I. So I'm going to go ahead and circle these. But there you go. There are the two numbers that when you square them, give you I. Notice that one of them is the opposite of the other, just the negative of that. But we already know that with square roots, right? Like think about the square root. When we take a square root of, say, 16, we always write plus or minus 4. That's the same thing. These are plus or minus root 2 over 2 plus root 2 over 2 I. Okay, so the process isn't terrible, but it's definitely weird. We're not used to thinking about trying to find square roots of complex numbers, but this is how we do it. Let's real quick, just for some practice, let's plot these two. Let's put them on the complex plane, just to help us remember how to do this. So basically, it's as easy as drawing the points, root 2 over 2, root 2 over 2. Okay, so that's going to be over here. So this is root number 1. It's a distance of 1 away. Remember how we had the square root of 1. So it's 1 unit away, but in that direction, in the direction of pi over 4. The other one, minus root 2, that's down here. We'll call that guy R2. But there are your square roots. All right, so we just found the square root, the two square roots of I. All right, well, let's do another one. Let's go to cube roots, and I'm pretty sure that I left this one as the hook for you last time, about the cube root of 8. All right, I ask you the cube root of 8, and you probably all immediately go, oh, that's 2. The cube root of 8 is equal to 2. All right, and so we know that that is true, because if you take 2 and then you multiply by 2 and then by 2 again, you get 8. But it turns out that there are 2 more.
we're going to find them. So first of all, how do I know that there are two more? Well, there's a fun little fact. This is actually called the fundamental theorem of arithmetic. I think this was Gauss, Johann Friedrich Gauss, or sorry, Carl Friedrich Gauss came up with this. But basically what it says is that there are n roots. So n roots for the nth root of x. So there's always as many roots as the kind of root that we're doing. All right, so Juan, yeah, in terms of the video, looks like at least other people are seeing it as well. But please let me know if mine definitely stops. We'll see if we can get it fixed. All right, so since it's a cube root, I know there are actually three. So like when we did square roots, we saw there was root 1 and root 2. Now when we do a cube root, there's going to need to be an R1, an R2, and an R3. Okay, but we're going to find it exactly the same way. So what we need to do is start by thinking about 8, just the number 8, plotting it so that we can figure out its modulus and its argument. All right, so here's the complex plane again. And so 8 is somewhere out here. It's a real number. So there you go, it's 8. So let's think about it. What's its absolute value? How far is it from the origin? All right, thanks, Eris. It's just 8. Okay, if z is 8, then the modulus of z is also 8. This is the nice thing about real numbers, is real numbers, their modulus is always themselves, or at least it's the absolute value, basically. All right, so then we also need to know a theta. So what's a good theta to pick? All right, thanks, Zeros. I like 0 as well. 0 is perfect. If you don't like 0, you could use 2 pi or 4 pi or 6 pi or negative 2 pi or whatever you want. All right, so there's what we know about 8. So in terms of the trig form for this complex number, we're going to have z equals 8 times the cosine of 0 plus I sine of 0. Yeah, we never take real numbers and write them in the trig form unless we're doing something like this. But you'll see why this is useful. All right, so let's go find our roots. All right, so here's how this is going to play out. Root number 1, it's going to be the cube root of 8 times the cosine of 0 divided by 3 plus I times the sine of 0 divided by 3. So if you go back and you look at de Moivre's theorem, right, we take the cube root of the modulus, cube root of 8, and then we divide by 3. Okay, well, 0 divided by 3, of course, is 0. The cube root of 8 is 2. So we have 2 times the cosine of 0 plus I times the sine of 0. And if we calculate those, cosine of 0 is 1, sine of 0 is 0. So we're left with 2 times 1, which is 2. All right, well, that was the one that we knew. We knew the cube root of 8 was going to be 2, so that's 2. So now let's go get the next one. So R2, again, we're going to take the cube root of 8. And what's going to change in here now is instead of 0, we're going to do 0 plus 2 pi. So in that formula that I wrote out, that would be k equals 1. So it's going to be 0 plus 2 pi. So we have 2 pi over 3. So we have 2 times cosine of 2 pi over 3 plus I sine of 2 pi over 3. And again, those are numbers that we know. Those are on our chart. We can evaluate them. So the cosine of 2 pi over 3 is minus 1/2. And the sine of 2 pi over 3 is root 3 over 2. I'm going to go ahead and multiply that minus 2 through, and we get negative 1 plus the square root of 3 times I. So this is also a cube root of 8. So we already knew 2, but now we've also got negative 1 plus root 3I. So if you were ever told, and I wouldn't be surprised if you were at some point, if you're ever told that there was only one cube root, you were kind of being lied to. It's really more a lie of omission. There's only one real root. Right? There are some that are complex, and here is one of them. All right, so there's R2. So then R3, well, same deal. I have the cube root of 8. But now, instead of 0 plus 2 pi, we're going to do 0 plus 4 pi. And so the same thing here, 0 plus 4 pi over 3. Okay, well, that's going to give us 2 times the cosine of 4 pi over 3 plus I sine of 4 pi over 3. And again, those are numbers that we know. They're negative 1/2 and negative root 3 over 2. So when I multiply by minus 2, I get negative 1 minus root 3I. Right up here. And so here is your third square root of 8. So if you take any of those 3 and cube them, you're going to get 8 each time. All right, so this is really, excuse me, why we care about this trig form of complex numbers, this polar form, because it really helps in this case in finding roots. And in later math, for those of you that are thinking about being math majors at all, you will definitely see this again. There's a branch of math called complex analysis, where you go into this a lot. But even if you don't go that far, you'll see this. Finding roots of numbers is important in like linear algebra, differential equations, and things like that. And those are classes that non-mathematicians still take, like engineers and physicists and so on. So. But anyway, so there you go. There's de Moivre's theorem. That's how we can find, excuse me, roots of complex numbers. Before we leave this, I just want to show you one more thing. I want to graph them all so you can see something, because there's kind of a nice pattern here when you look at roots. So we already saw that one of the roots was 2. That was over here. There was also one that was negative 1 plus root 3I. So that would be like right up there. And then there's also -1 minus root 3 pi. So that's going to be like down here. And I just want you to notice that where those roots are divides the circle up. I pretend that's a circle. But divides it up into 3 equal pieces. So the roots always have the symmetry. Excuse me. So if you find 1, you can actually speed up the process a lot by just going, all right, let's take that full 2 pi and divide it into chunks and then just keep moving it. So think about what we had. We had 2 pi and we divided into 3 chunks because it was a cube root. And you can even still see it on the board. Here's your 2 pi over 3. And then another one of those gets us a 4 pi over 3 and so on. So that's why we're seeing it is really just the structure of how the Mob's theorem works. All right, so any questions on that one before we move on?
All right, so there's the last little bit I wanted to show you about complex numbers. And if you just kind of pause for a second and think about what we've been doing the last couple days, this now feels completely different. Like these are completely different things than measuring triangles, and yet it still comes back to right triangle stuff. So this is one of the reasons why trig is everywhere. As soon as you can, if you can create a right triangle or a circle, trig is going to show up. So complex numbers, polar coordinates, they seem completely different, but they're really the same thing. We're just applying it to different ideas. Okay, so for the rest of today, I'm gonna introduce you to what we call vectors. So just so you know, if you're playing along at home, I'm skipping a section. My intention is to come back and talk about it on Wednesday, but if we run out of time, I'd rather lose the section on parametric equations than the one on vectors. So I'm going out of order of the book, just so you know. I think this is 10.5 maybe, but we're going to go to vectors, skip parametrics for now. Okay, so vectors, what are those? Now, vectors, again, knowing that you guys are all going to be taking calculus and probably most of you are going to be taking physics, vectors are huge. They are absolutely huge in the real world, in the applied world, places where we use math. And here's what a vector is. A vector is something that has not just a number attached to it, not just a magnitude, but also a direction. Okay, so if we have a quantity where the direction matters, we need to use a vector. So you may remember earlier when we were talking about the modulus, how far away we were. And I think it was Erez asked, it doesn't matter which direction. Since the answer to that was no, that's not a vector. Okay, that's not a vector. We have a name for those. We call them scalars. I'll write this on the board in a second. But a scalar is just a number like you're used to. Okay, but a vector needs a direction. So let me give you an example. A really good example from physics is forces. Now, forces are pushes and pulls. Okay, so like if you push something or you pull something, you're applying a force. The direction that you apply that force absolutely matters, right? So imagine you were standing right in front of me and I gave you a shove. You're going to fall backwards because I just pushed you. Now, if instead of pushing you, if I grabbed you and pulled you, the same amount, like I'm not going to pull you any harder than I pushed you or anything like, so it's the exact same amount. There's going to be a different result for you though, because now instead of falling backwards, you're going to fall forwards, right? So there's a different result because I applied that force in a different way. Or what if I came and pushed you from the side? Now you're going to topple over on the side, which is different, right? So that's an example of a quantity where the direction matters. Okay, so force is a great example. Velocity, which is different than speed. All right, so speed is a scalar. So if you say you're going 25 miles an hour, that's a scalar. But if I say I'm going 25 miles an hour that way, that's a vector. All right, so all kinds of things are vectors. As soon as we include a direction, it's a vector. So no direction, scalar, direction, vector. So there are lots of things out there that are both. Temperature is a scalar, right? I'm not going to say if someone says, oh, how hot is it? I'm not going to go, it's 25 degrees C in that direction. No, it's 25 degrees C. That's our temperature, right? So age, right? If you say, okay, I'm 47. I'm not 47 going that way. I'm 47, right? So those would be scalars as opposed to vectors. All right, so let's go to the board and let's talk about how we represent vectors.
All right, so again, let me just recap what I just said. So vectors, these have a magnitude, so a number attached to it, and a direction. Otherwise, we call these scalars, and these are magnitude only. All right, so how do we represent a vector? It's actually really easy. We do this in two ways. One way that we can represent vectors is graphically. So let me put here graphical vectors. And what we use when we want to represent a vector is an arrow. Okay, so there's an arrow. The reason we use the arrow is because it's pointing in a direction. All right, so the arrow shows direction. So the wind is blowing that way, or I'm pushing on the door that way, or whatever kind of thing that I need to show direction with. So the arrow just shows you the direction. So, okay, there's half of it, right? The other part we have to show is the magnitude. And the way we show the magnitude is by changing the length. All right, so the length equals the magnitude. So again, if we're going to talk about like a force, so I'm pushing you. If I push you softly, okay, just a nice little gentle nudge, that's going to be a really short arrow pointing in that direction. But if I slam you, that's going to be a long arrow pointing in that direction. All right, so that's how we show magnitude and direction. Length gives us magnitude, and where the arrow points, that gives us the direction. So not a big deal. It's pretty easy. Before we go too far, though, let me give you some terminology in terms of the vector. So the length of the vector, the magnitude, the way that we actually show that, well, let me start here. In terms of vectors, if you want to demonstrate that you have a vector, I'm going to use the letter V to be my generic vector here. We always draw a little arrow over it, or I will always draw a little arrow over it to show you that it's a vector. If you look in the book, and a lot of other places, they'll make it bold, and bold will mean that it's a vector. but I can't really differentiate between bold and not bold on the whiteboard. So I'll draw a little arrow over it to tell us that it's a vector. Okay, so this is a very standard notation. This is not just a Bruceism. This isn't something that I do just because it's me. No, this is something that's always done. Okay, so this is our vector. And so when we talk about its magnitude, the way that we're going to represent that is with a double absolute value. I have no idea why they chose a double absolute value, but that is the standard. So if you ever see that, that's just saying, all right, how long is that vector? What's its magnitude? There's also another name for this. It's also called the norm. So if you ever see anything and they say, what's the norm of a vector? Again, it means the same thing. What's the magnitude? There are going to be plenty of times when I'm talking that I will say norm. That's kind of it's one of those things that is kind of standard. So I'll say that a lot. So just realize if I say norm, I mean its magnitude. All right, so cool, no big deal. That's all you got to do to show a vector. Now, the other way that we show vectors, represent vectors, I'll get there in a minute. But before we do that, I want to show you how we do the operations on vectors. Okay, so like what it means to add and stuff like that. All right, so to add vectors, what you're going to do is you're going to attach them. You're going to line them up. And I'm going to say here, head to tail. So let me give you, I'm going to show you an example as we kind of go through here so you can see what I mean. So let's say that these are two vectors. We'll have the vector u, which let's say u points in that direction with that length. And then we'll have a vector v, but v is going to point down, and let's make it kind of shorter. Let's say it points like that. Okay, so there's u and there's v. So here's what we're going to do. If we want to add them, when I talk about the head of an arrow, that's the tip where it's pointing, right? The arrowhead. And then the tail is the other side. So what I'm going to do is I'm going to take the head of u and make sure that it lines up with the tail of v. So basically, I'm going to take this guy, think about this v, I'm just going to move it so that it's over here. Because fun fact about vectors, we don't care where they are. It's irrelevant. The only thing that we care about is how long they are and what direction they point. So these are actually the same vector. I know it's weird. I mean, I could have 100 arrows that are all pointing that direction on the board, and they're all the same vector. But there we go. So I just line those things up head to tail. That's what I mean by step number one. So then step number two is now we're going to create a new vector. We call it the resultant. So the resulting vector by connecting the new head and tail. So the new head and tail, well, the new head is right here at the end of V. Because imagine I'm just following the black arrow and then I go to the blue arrow. And the new tail is the original tail, so I just go ahead and connect those. So there is the vector u plus v. So you just line them up and then connect the open ends, and that's your resulting vector. So not really a big deal, but you can imagine that it's kind of a pain in the butt. Make sure that you transfer this so it's exactly the right direction and exactly the right length, because mine, I guarantee you, isn't. Excuse me. But once we've got them, that's all we got to do. All right, so there's adding vectors. Subtracting vectors, there isn't actually such a thing. I mean, there is, but there isn't. Subtracting is really adding negatives. So instead of showing you this is how we subtract, I need to show you what does it mean to multiply. All right, so we'll take a vector times a number. All right, so this is the process graphically, how we add vectors. Okay, now multiplying, here's kind of a catch. There are actually 3 kinds of multiplication for vectors. Yeah, there's actually 3 kinds. But the one I'm going to show you is what we call scalar multiplication. And scalar multiplication, this is going to be when we have some number c times a vector. So notice I did not put an arrow over the c. It is not a vector, it's just a scalar. It's your good old friend like 2, negative 14, right? Any old number that you know and love. Okay, so we're going to take that vector and we're going to multiply it by that scalar. Okay, so here's what you do. Is the resulting vector points in the same direction. Okay, so really, in this case where I say it's pointing in the same direction, this is if C is positive. I'll show you what happens if C is negative in a second. But the resulting vector points in the same direction, so it's not going to change direction. But the magnitude changes. What you do is you just take the magnitude of the original vector, so the magnitude of V, and multiply it by C. So like if C was 2, what we just did was we took our vector and we made it twice as long. If C is 10, our vector is now 10 times as long. If C is a quarter, it's now 1/4 as long. Okay, so that's all scalar multiply does, is changes the length. It doesn't change which direction it's heading. Okay, and that's again if C is greater than 0. So let me show you an example real fast. Like let's say that this is our vector V. So if we had, say, 3V, it's going to be this same direction, just 3 times as long. So let me draw an arrow that's parallel, so it's going the same direction. And let me just make sure that it's 3 times as long. All right, but notice that each of those places between the little tick marks is the same length as the original. So that'd be 1V plus another V plus a third V. And if you think about what multiplication means and the fact that it's repeated addition, this makes total sense. I'm going to take V plus V plus V, so I need to line them all up. Well, they happen to all point in the same direction, so I just increased my length, right? Or let's do a half of a V. So again, you need to be parallel. Parallel. I don't think that is either. How about call that close enough. But now I need it to be half as long. So this would be 1/2 v. Again, pointing in the same direction. It's just been shrunk by half. Okay, so that's what's happening with the scalar multiplication if the scalar multiple is positive. Now, if it's negative, I bet you can guess what happens. What do you think happens if we take a vector and we multiply by a negative? Yeah, so Era just put in opposite direction with the question mark. I'll change that to an exclamation. Yep, it goes in the opposite direction. So if C is negative, the vector flips and points the opposite way. So it's still parallel, it's just pointing the other direction. So let's do another one up here, say -2v. So we're going to have our line, start our line that's parallel to all the rest. It needs to be length 2. Okay, so make sure it's length 2. But now instead of pointing down, this one's pointing up. Okay, so that's the only difference. If C is negative, it actually points the opposite direction. Okay, so then what do you do if you get C equals 0? What do you think that means? Like, what if I took 0 times a vector? So as you say, we get no vector. It's not quite true, but you're on the right track. If C equals 0, we just get a point. This is really a vector of no length. And this is where mathematicians get a little bit weird. Just because it has no length doesn't mean that it doesn't exist. Okay, so I know this is weird because we're not used to that in like the real world. But mathematicians have plenty of things that have no length. We call them points, and points kind of matter. But what we end up getting is a point. Okay, so error is you can say if there's no direction, how's it a vector? Well, it still does have direction. Basically, it'd be like me saying, okay, go that way, no steps. Or go that way, no steps. Or go that way, no steps. It just turns out we can attach all kinds of directions to it if we want. All right. We actually call this the 0 vector. So we use a little arrow over the 0. Okay, so this is what we call the 0 vector. But it does the same thing as the number 0 does. You add the 0 vector and nothing changes. If you add two vectors that are opposites, so they point in opposite directions but the same length, you get the 0 vector. Starts and ends at the same point. And the 0 vector is actually important, even though it doesn't feel like a vector. All right, so this is probably the weirdest vector, well, that you're going to see until you get to like linear algebra. This is like the weirdest vector that we had to deal with, the 0 vector, because it feels wrong in a couple of ways. One, that there is no length to it, and the other, with the direction, the fact that, well, can't it really be pointing any direction? So then no direction, right? So it is an interesting creature, but it's still an important vector. It's just the point. The head and tail of the vector are at the same location. right, now, I had to show you this to show you how we do subtraction. Because if we want to subtract two vectors, what we think of them as is an addition problem, but adding the opposites. So like, let's say I wanted to do u minus v. We're going to think of this as u plus negative v. And negative v looks just like v. It just points in the opposite direction. So again, let me show you how this works graphically. So let's go with, here's u. And let's go with, say, this is v. Let me change color. Okay, so there's v. Now, what I want to add to u is not v. I want the opposite of v. So the opposite of v is parallel, just points in the other direction. So that's the one that I'm going to put here on the end. So u minus v is the same as u plus negative v. And so again, I connect tip to tail. And so this is u minus v. So that's why I said there really isn't subtraction, because we're still using the addition process. We're just adding the negative. All right, so there's adding, there's subtracting, and I also just showed you scalar multiplication. Now, I did tell you that there are two other kinds of multiplication. Let me just go ahead and put this up here so that we're complete. I'm not going to show them all to you. I'm going to show one of them to you. Okay, so key, multiplications. All right, so the first one is scalar multiplication. We just saw that. That's the one that changes its length, possibly changes the direction if it's negative. Okay, then we have what we call the dot product. And we've got the cross product. All right, now these are called the dot product and the cross product because the multiplication symbols we use are either the dot or the cross. So this is one of those places where it matters which one we do. And this multiplication is between two vectors. Okay, so for both of these, we're taking two vectors and we're multiplying them together. The first one, the dot product, that actually gives a scalar. So when you take two vectors and you dot them together, you get a scalar. When you cross two vectors, the result is another vector. So basically, these two multiplications work such that when you multiply one way, you get just a scalar, the other one you get a vector. Now, we didn't have to worry about that before because we only ever had scalars. There weren't other options, right? Now we've got options. So I will show you the dot product in a little bit, but I'm not going to show you the cross product. We're going to save that for calculus. Okay, so we got three multiplications. So then you're probably thinking, oh, good Lord, how many divisions do we have? Well, here's some good news. There is no such thing as vector division. And that should make everybody excited, because that's one less thing we have to worry about. right? So we're not going to actually divide. Now, you can divide by a scalar, right? We kind of did, right? When we had like a 1/2 v, we're dividing by 2. That's the same as multiplying by 1/2. So you can divide by a scalar, but you can't divide by a vector. There's no such thing as u divided by v. Okay, so good news, I guess. All right, well, anyway, so that's how we do all this stuff graphically, but you can probably imagine that it's kind of a pain in the ass to try to do this stuff graphically. Especially if I gave you a bunch of vectors, they've got really long lengths. If our angles are not perfect, you can see that it might be a bit of an issue. So we actually have another way of dealing with vectors, and that is by breaking them into what we call components. So let me show you this. And the best way to describe it is to draw a picture, kind of like we always do. Okay, so here's our plane, and since it doesn't matter where the vector is, let's just go ahead and start it here at the origin, and we'll send it off this way. Okay, so this is V. Now what we can do is, instead of thinking about it as this one vector, let's think about taking two vectors and adding them together such that they give us this vector. But I'm going to pick nice vectors. I'm going to pick vectors that point in the x direction and vectors that point in the y direction. And so what I know, like if this is the vector v, right, we'll call the red one v. Just for right now, I'm going to give these names. Let's call the black one, say, A, and the green one, B. Then what I know is that the vector V is the sum of those two. Right? Because I'm lining these things up tip to tail, and that's how addition works. All right, it's probably at about this point you're seeing the trig. You're going, oh my God, we've seen this picture so many times. We saw it first when we were talking about right triangles in the unit circle definition. And we saw it again when we were talking about polar coordinates. And then we saw it again when we did complex numbers. And now we're seeing it again with vectors. Yeah, you get this picture. That's why this is part of trig. Right? So these guys, A and B, these are called the components of V. Okay. A, this is the x component. And B is the y component. All right, so we've got this. Now, the way that we write this then, we can actually describe this vector only in terms of its components. And so here's how this is going to work. You're going to see two different ways that this is written. You're going to see either AI plus BJ. I'll explain that in a second. Or you're going to see it written like an ordered pair, but with pointy parentheses. So that's what tells you it's a vector, not like a point. And we just put the components in their order, x and y. Okay. Now, you're going to see me write it the second way, pretty much exclusively, because it's faster, takes less writing, I'm lazy, I don't want to do more. I'm not actually certain how the book shows it, Okay, so just be aware that they do mean the same thing. Now, I did throw in this I and this j, and you must know that this is not the complex number I. Okay, it's a vector. But the vectors I and j are what we call unit vectors. A unit vector, all this means is it's a vector of length 1. Okay, so it's just a vector of length 1. Now, I and j are unit vectors. It's the unit vector that points in the direction of positive x. J is the unit vector that points in the direction of positive y. So now you can see why we write the components as a times I and b times j. A changes the length, right? It takes that horizontal one and changes the length to whatever we need it to be. The b changes the length on the vertical one. And then we add them together. Well, those are our components. All right, so you're going to see it in one of those two ways, but that's what the components are. They're just telling you which direction to go. All right, well, what's kind of nice about this then is that if you're in component form, the operations are crazy easy. And you don't have to worry about drawing. You don't have to worry about how good of an artist you are or how precise you can be or anything. Let me show you how these work. Okay, so I'm going to start with scalar multiplication. If you do C times V, right, and let's say that V, let me write it just so it's A times or AB, right? So then C times V is just CA and CB. You just multiply those components by whatever that scalar is. Done. Done. It's that easy. If you want to add, so let's say we've got two vectors here. Let's say V is equal to A comma B, and U, let's say that that's equal to C comma D. Then V plus U, you literally just add the components together. If it's subtraction, you're adding the opposite. Well, that ends up being A minus C, B minus D. All right. So it's that easy. Let me show you some examples. So let's say that U is 1, -3, and V is -2, 1. Okay, so just two random vectors. And let's do some things to them. All right, so for example, let's say we have -2U. Well, you just take the components of U and multiply them both by -2. And there you go. It's -2, 6. Let's do U minus V. So we're going to take the components and subtract the one from V, the V1 from the U. So this is going to give us an X component, 1 minus -2, which is 3. And then the Y component is going to be -3 minus 1, which is -4. So it's way easy. Okay, doing operations are not difficult now if we're in the component form. And you can have all kinds of different combinations of this stuff, and it's still all good. Like, let's say we did 3u plus 4v. Okay, well, we'd start by multiplying u by 3. So 3 comma minus 9. Multiply v by 4. That's going to be minus 8 comma 4. And now we add those together. 3 plus -8 is -5. Minus 9 plus 4 is -5. And there's the resulting vector. So I'm a big fan of what we call the rectangular form for vectors. I love this because it's super easy to do calculations on. But I want you to think about the point of vectors. Right? The whole point is to know how long they are and in which direction they head. That's not really clear necessarily when we have something like this. So what we need to do is work on some sort of way to actually find the magnitude and the direction. Well, here's the good news. Let's just plot this one, for example. So we just found this vector that was -5, -5. So if I started at the origin, I need to go -5 in the x, and then -5 in the y. Right? So that brings me down here. So here is my vector, -5, -5. All right, that's this guy, 3u plus 4v. All right, so again, I'm curious about its magnitude and its direction. Well, you remember polar coordinates, I hope, because that was not too long ago. Wasn't that the whole point of polar coordinates? Figure out a distance and a direction? Well, that's exactly what we do here. All right, so if I want to know the magnitude, say, of 3u plus 4v, I just need to know how far away is this point? Well, if you remember from your polar coordinates, r squared is equal to x squared plus y squared. So there you go. This is going to be the square root of 50, 25 plus 25, which is 5 root 2. So this vector has a length of 5 root 2. And I also need to know its direction. Well, that's easy enough to get because this is a nice angle. But even if it weren't a nice angle, remember how we find it. We know the tangent of theta is equal to y over x. So in this case, -5 over -5, which is 1. Well, if I do inverse tangent, I'll get pi over 4. But pi over 4 is in the wrong quadrant, so I got to add pi. Right? So what I've got then is, in this case, that theta is 5 pi over 4. So if you're in rectangular form, you can still find magnitude and direction. You're just using the polar conversions. So let me just formalize this for those of you that like to have the little formulas and stuff. So if our vector has components a and b, then the norm, the magnitude, is going to be the square root of a squared plus b squared. And the direction is going to be found by using tangent. It's the tangent of b over a, which was exactly what we did with polar coordinates, which is exactly what we did with complex numbers. So even though it feels like we're doing something completely different, it's not. They're all really interrelated. All right, so that's how this whole rectangular form, the component form of vectors, works. And it's super, super nice. Makes it a lot easier to do calculations. All right, so what I want to do with the last little bit of time today is I want to show you the dot product. And the dot product is pretty easy. Most people like it, especially if you're in the component form. Trying to do it otherwise is kind of a pain. But here's how you do the dot product. So let's just say we've got a couple of vectors here. So U will be A and B, and V is going to be C and D. Here's how we take the dot product. You're going to take the X components, A and C, and you're going to multiply them. You're also going to take the Y components and multiply them, and then just add those two numbers together. That's it. So it's actually pretty fast and pretty easy. So let me give you an example. Let's say U is 1 minus 3. I think that might have been the same U we used before. And let's say that V is 2, 4. So if I dot them, U dotted with V is going to be 1 times 2 plus negative 3 times 4. So that's 2 minus 12, or negative 10. So the dot product of those two vectors is negative 10. Notice that it is a scalar. It's just a number. And it's just negative 10. All right, so easy, right? Really easy when we're in component form. And it's usually at about this point people go, okay, what the hell does that negative 10 mean? Well, that's a very deep subject, all the different things that the dot product gives you. But let me show you what we can use it for right now. But to show you that, I need to show you geometrically what happened. So the dot product, another way of thinking about the dot product, if you think about it more geometrically, what you end up getting is actually the product of the two magnitudes. So if you just think about it, if we've got longer vectors, their dot product is going to be greater. But there's also a term here, a cosine of theta. And what theta is the angle between the vectors. So let me just draw a picture here. Let's say that this is U. And let's say we now, instead of lining up head to tail, we'll put their tails together. So let's say that maybe this is V. Then the theta is this angle right here, the angle between U and V. All right, now where this comes from, I'm not going to prove it, but I will just tell you that where it comes from is the law of cosines. You remember your law of cosines. Notice we've got side, angle, side, basically. And that's a law of cosines kind of deal. So law of cosines is what leads to this. All right, now what we're going to use the dot product for is to actually find that angle. Okay, so when I'm going to put here a list uses of the dot product. And first and foremost, this is going to be to find angles. Because if you know the two vectors, you can actually calculate their magnitudes and all that and actually solve for the cosine. Okay, so that's the first, and that's probably the biggest use of the dot product. But then I'm just going to put here a list too long to write. It's a huge list. And the more math you learn, the more places you see where you use the dot product. I'm teaching differential equations right now, which is our last math class that we offer for students before they transfer. And the dot product shows up in there. It showed up in linear algebra, the class before that. It shows up in vector calculus. Go figure, fourth quarter calc. And I think it even shows up in third quarter calc. So we're going to see the dot product in lots of different places. But let me just show you real quick how we can calculate the angle between two vectors. So here are two vectors. Let's call them, again, u and v. Getting tired of using the same one. Let's see if I can get a little more creative. How about -2, 4? That'll be u. And let's say, let's make v 6, 3. All right, so if we use this formula up here to find the cosine, we're going to see that the cosine of the angle in between them is equal to u dot v divided by the magnitudes of u and the magnitudes of v. Okay, I just divided those two numbers over. Magnitudes are numbers, or scalars, so I can divide them. All right, so we need to do three things here. We need to get their dot product, and we also need to get their magnitudes. So let's start with the magnitudes. So the magnitude of u is going to be the square root of -2 squared plus 4 squared, which is the square root of 20. And I'm just going to leave it like that for right now. I don't worry about rationalizing if I'm just going to find an angle. I also need the magnitude of v. All right, well, that's going to be the square root of 6 squared plus 3 squared, which is 36 plus 9, or 45. So that's the square root of 45. So in terms of this formula, we've got the cosine of theta equals, on the bottom, we're going to have the square root of 20 and the square root of 45. It's very rare that these numbers work out nicely. So this is usually something that we definitely need to use a calculator for. All right, but now let's get u dotted with v. So if we do u dot v, again, take the x components and multiply. So -2 times 6. And then we're going to add the product of the y components. So 4 times 3. So -2 times 6 is -12. 4 times 3 is 12. -12 plus 12 is 0. So these two, their dot product is 0. So we'll put a 0 up on top. All right, so now if we take 0 divided by these things, that does equal 0. 0 divided by any non-zero number is 0. All right, so now what angle does that give us for theta? What angle makes cosine equal 0? Thanks, Adam. That tells us that theta is pi over 2. So the angle that's actually between those vectors is pi over 2, which is a right angle. These two vectors are actually perpendicular to each other. Let me try to draw them kind of decently so you can see it. So u -2, 4. I got to go left 2 and up 4. So that looks like U. V is 6, 3. So that's somewhere like that. And you can see that they do form a right angle. All right, well, let me show you a little bit of a shortcut for that to know that they're right angles. Because for it to be a right angle, we need this fraction to equal 0. Well, the only way that can happen is if the top is equal to 0. So here's just a fun little fact. If U dotted with V equals 0, then they are orthogonal, or sorry, perpendicular. I just threw a linear algebra term in there. I apologize. I just said orthogonal. Ooh, scary. It just means perpendicular. So if U dotted with V is 0, then they're actually perpendicular. It turns out that the sign of U dot V is what's important when we're talking about angles. If U dotted with V is positive, then the angle is acute. So it's going to be a small angle, and they're going to be closer together than 90 degrees. And if U dot V is negative, then the angle is obtuse. So when I'm doing one of these, the very first thing I do is the dot product. And I look at its sign. If it's 0, I go, okay, cool, they're perpendicular. If it's greater than 0, then I know that they're going to be acute. Negative, they're going to be obtuse. But then I know at least the size of that angle, right? I still don't know exactly what the angle is until I do the complete calculation, but at least I do know which side of 90 degrees we're on. Okay, so I think I'm going to stop here, but of course I do need to give you the word of the day. So I think today's word of the day, because I don't think I've used this yet. Let's go water. I got a jug of water here. So today's word of the day is water. Good old H2O. All right, so real quick for next time. Hold on, let me change my screen.
So you guys can see me instead of the whiteboard if you're watching the video. So next time, I know I said we were going to have a quiz. I've decided we're not. Okay, so no more quizzes. I'll still drop your lowest quiz score and all that from the ones in the past, but we're not going to do a quiz on Wednesday. On Wednesday, I'm going to talk about parametrics and then answer any kind of questions you guys have on the vectors and all that. So that'll be Wednesday. And then our final exam is coming up next week, right? In terms of how that's all going to play out, we'll talk about that on Wednesday in terms of timing and my expectations and what's going to be on and all that good stuff. Okay, so we'll talk about that on Wednesday. But anyway, so that's what I got. Any questions or concerns before we call it a day? So next week, Adam, we only have the final exam. So like I said, I'll let you know the scheduling of it because we might adjust it slightly. But basically, I'm going to turn on the exam. You'll have the time to take it and turn it in, but that's the only thing we're doing. Yeah. So, and yes, William, I did say I dropped the lowest quiz score. If you look at the syllabus, I dropped everybody's lowest quiz score. All right, any other questions?